interpretation of the code requirement is correct. The National Electrical Code, or NEC, does not specifically state whether neutral conductors should be counted as current-carrying conductors for the purposes of derating. However, the generally accepted practice is to count them, as they do carry current under normal conditions, especially in multi-wire branch circuits serving nonlinear loads. In the described scenario, there are 7 current-carrying conductors. These are comprised of 5 hot conductors, 2 neutrals, and 1 ground. Note that the grounding conductor is typically not considered a current-carrying conductor for derating purposes, but the neutrals in a 120/208 volts 3-phase system are. According to Table 310.15, B2. This number of current-carrying conductors requires derating the allowable ampacity of the conductors. Table 310.15, B2. Provides adjustment factors for the allowable ampacities of conductors in a raceway or cable with more than 3 current-carrying conductors. The adjustment factor for 7 to 9 current-carrying conductors is 70%. Table 310.16 indicates that the maximum allowed ampacity for number 12 THHN, assuming it is rated for 90 degrees Celsius and used in a system where the terminations are rated for at least 75 degrees Celsius, is 30 amps. However, it's crucial to note the conditions of use and the temperature ratings of the equipment and conductors. If the terminations are only rated for 60 degrees Celsius, the ampacity must be based in the 60 degrees Celsius column, which is typically lower. Assuming the 90 degrees Celsius rating, 70% of 30 amps is 21 amps. However, a footnote to Table 310.16 refers to Section 240.4. D, which contains specific overcurrent protection requirements for number 14, number 12, and number 10 copper conductors. Specifically, 240.4. D states that the overcurrent protection device, or OCPT, cannot exceed 20 amps for a number 12 conductor. In this case, the overcurrent protection required by 240.4. D is less than the derated circuit calculation by 1 amp. The derated ampacity was calculated to be 21 amps, but the maximum allowed overcurrent protection is 20 amps. Therefore, there is no need to take additional measures to derate the circuits in this case, as the requirements of 240.4 D effectively accomplish the same thing. The 20 amp overcurrent protection will protect the number 12 conductors even with the derating factor applied due to the number of current-carrying conductors. To further clarify, the application of derating factors and overcurrent protection requirements ensures the conductors are protected from overcurrent conditions. The NEC provides these rules to prevent overheating and potential fire hazards. In this specific scenario, the 20 amp overcurrent protection dictated by 240.4 D is more restrictive than the derating calculation, making the derating calculation somewhat redundant. However, it's important to perform both calculations to ensure compliance with all applicable code requirements. Also, it is very important to correctly identify all current-carrying conductors. Neutral conductors in a 3-phase, 4-wire system are generally considered current-carrying conductors. Grounding conductors are generally not considered current-carrying conductors for derating purposes. There can be more complex situations, such as when dealing with harmonic currents on a neutral of a 3-phase system. In such cases, the neutral may carry significant current and must be properly sized and considered for derating purposes. The NEC provides guidance on these situations as well. The key takeaways are: firstly, accurately determine the number of current-carrying conductors in the raceway. Secondly, apply the appropriate derating factors from Table 310.15. B2. Thirdly, ensure the overcurrent protection does not exceed the values specified in 240.4 D for the given conductor size. Finally, always consult the latest edition of the NEC and seek guidance from a qualified electrical professional when in doubt. Remember that local amendments to the NEC may also exist, so it is crucial to verify the applicable codes and regulations in the specific jurisdiction. Proper application of these rules ensures a safe and compliant electrical installation. Conductor ampacity is the maximum current, in amps, a conductor can carry continuously under the conditions of use without exceeding its temperature rating. Several factors influence the ampacity of a conductor. These factors include firstly the conductor material. Copper and aluminum are the most common conductor materials. Copper generally has a higher ampacity than aluminum for the same size conductor. Secondly, the conductor size. Larger conductors have a greater cross-sectional area and therefore can carry more current. Conductor size is typically expressed in American wire gauge or AUG, or in circular mills. Thirdly, the insulation type. Different insulation materials have different temperature ratings. Common insulation types include THHN, THWN, XHHW, and others. THHN is a common thermoplastic high heat resistant nylon coated wire. THWN is a thermoplastic heat and water resistant nylon coated wire. XHHW is a cross-linked polyethylene high heat and water resistant wire. The temperature rating of the insulation determines the maximum temperature the conductor can withstand. Fourthly, the ambient temperature. Higher ambient temperatures reduce the ampacity of a conductor. The NEC requires adjustments to ampacity for ambient temperatures above 30 degrees Celsius or 86 degrees Fahrenheit. Fifthly, the number of current-carrying conductors in a raceway or cable. As previously discussed, multiple current-carrying conductors in close proximity can raise the temperature of required derating. The NEC provides tables to adjust ampacity based on the number of conductors. Sixthly, the installation method. The way a conductor is installed, such as in free air, in a conduit, or direct buried, affects its ability to dissipate heat. Different installation methods have different ampacity ratings. Overcurrent protection is the use of devices such as circuit breakers and fuses to protect electrical circuits from excessive current. Overcurrent can result from overloads, short circuits, or ground faults. Overcurrent protection devices are designed to interrupt the circuit when the current exceeds a predetermined level. The NEC specifies the requirements for overcurrent protection based on the conductor ampacity and the type of load served. Circuit breakers are electromechanical devices that automatically interrupt the circuit when an overcurrent is detected. They can be reset after tripping. Fuses are one-time use devices that melt and interrupt the circuit when an overcurrent occurs. They must be replaced after they blow. The selection of the appropriate overcurrent protection device depends on several factors. These include firstly the conductor ampacity. The overcurrent protection device should be sized to protect the conductor from overcurrent. Secondly, the type of load. Different types of loads, such as motors, require different types of overcurrent protection. Thirdly, the interrupting rating. The overcurrent protection device must have a sufficient interrupting rating to safely interrupt the maximum available fault current at the point of installation. Fourthly, the coordination. The overcurrent protection devices should be coordinated to ensure that the device closest to the fault opens first, minimizing the extent of the outage. Conduit fill refers to the percentage of the cross-sectional area of a conduit that is occupied by conductors. The NEC limits the amount of fill allowed in a conduit to ensure adequate heat dissipation and to prevent damage to the conductors during installation. The maximum allowable conduit fill depends on the type of conduit and the number of conductors. The NEC provides tables that specify the maximum allowable fill for different types of conduits. Common types of conduits include firstly, electrical metallic tubing, or EMT. EMT is a thin-walled metallic conduit commonly used for indoor wiring. Secondly, rigid metal conduit, or RMC. RMC is a thick-walled metallic conduit used for both indoor and outdoor wiring. Thirdly, rigid polyvinyl chloride conduit, or PVC. PVC is a non-metallic conduit used for underground and corrosive environments. To calculate the conduit fill, firstly determine the cross-sectional area of each conductor. The NEC provides tables that list the cross-sectional area of different conductor sizes and insulation types. Secondly, sum the cross-sectional areas of all the conductors in the conduit. Thirdly, determine the internal cross-sectional area of the conduit. The NEC provides tables that list the internal cross-sectional area of different conduit sizes. Fourthly, divide the total conductor cross-sectional area by the internal cross-sectional area of the conduit. Finally, multiply the result by 100 to express the conduit fill as a percentage. The NEC also specifies requirements for the bending radius of conduits to prevent damage to the conductors. Bending conduits require specialized tools and techniques. Proper conduit fill and bending practices ensure a safe and reliable electrical installation. Neutral conductors play a critical role in electrical systems, particularly in three-phase systems. In a balanced three-phase system, the neutral conductor carries little to no current. However, in an unbalanced system, the neutral conductor carries the difference in current between the phases. Nonlinear loads, such as electronic devices and fluorescent lighting, can generate harmonic currents that flow in the neutral conductor. Harmonic currents can cause the neutral conductor to overheat if it is not properly sized. The NEC requires the neutral conductor to be sized to carry the maximum unbalanced load. In some cases, the neutral conductor may need to be larger than the phase conductors. The NEC also provides guidance on the use of neutral current sensors to detect and mitigate harmonic currents. Proper sizing and management of neutral conductors are essential for a safe and reliable electrical system. In summary, understanding the NEC requirements for derating conductors, overcurrent protection, conduit fill, and neutral conductors is crucial for electrical safety and compliance. These concepts ensure that electrical systems are designed and installed to minimize the risk of fire, electric shock, and equipment damage. Always consult the latest edition of the NEC and seek guidance from a qualified electrical professional when working on electrical systems. Electrical calculations are a fundamental aspect of electrical engineering and are essential for designing safe and efficient electrical systems. These calculations involve determining the appropriate conductor sizes, overcurrent protection, voltage drop, and other parameters to ensure that the electrical system can handle the intended load without exceeding its limitations. One of the most common electrical calculations is determining the conductor size required for a particular load. This involves considering the ampacity of the conductor, which is the maximum current it can carry continuously without overheating. The ampacity of a conductor depends on several factors, including its material, size, insulation type, and the ambient temperature. The NEC provides tables that list the ampacity of different conductors under various conditions. Once the ampacity of the conductor is determined, it is necessary to apply derating factors if there are multiple conductors in a raceway or if the ambient temperature is high. Derating factors reduce the allowable ampacity of the conductor to account for the increased heat generated by multiple conductors or high ambient temperatures. Another important electrical calculation is determining the appropriate overcurrent protection for a circuit. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the circuit from excessive current that can cause overheating and fire. The overcurrent protection device should be sized to protect the conductor from overcurrent without nuisance tripping. The NEC provides guidelines for selecting the appropriate overcurrent protection device based on the conductor ampacity and the type of load served. Voltage drop is another important consideration in electrical calculations. Voltage drop is the decrease in voltage along a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that the voltage drop in a branch circuit should not exceed 3% and the voltage drop in a feeder should not exceed 5%. Voltage drop calculations involve determining the resistance of the conductor and the current flowing through it. Other electrical calculations include determining the short circuit current, ground fault current, and the size of the grounding conductor. These calculations are necessary to ensure that the electrical system is properly protected from faults and that the grounding system can effectively carry fault current back to the source. Electrical calculations can be complex and require a thorough understanding of electrical theory and the NEC. It is important to use accurate data and to follow the NEC guidelines carefully to ensure that the electrical system is safe and efficient. In addition to manual calculations, there are many software tools available that can assist with electrical calculations. These tools can automate many of the tedious calculations and can help to ensure accuracy. However, it is important to understand the underlying principles behind the calculations and to verify the results of the software. Proper electrical calculations are essential for designing safe and efficient electrical systems. By following the NEC guidelines and using accurate data, it is possible to ensure that the electrical system can handle the intended load without exceeding its limitations. Always consult with a qualified electrical professional when designing or modifying electrical systems. They can help to ensure that the system meets all applicable codes and standards. Furthermore, understanding electrical theory is paramount to performing accurate and safe electrical calculations. Key concepts include Ohm's law, which relates voltage, current, and resistance, and Kirchhoff's laws, which describe the conservation of current and voltage in electrical circuits. A solid grasp of these principles is crucial for analyzing and designing electrical systems. The National Electrical Code serves as the cornerstone for safe electrical installations. It is updated regularly to reflect the latest advancements in technology and safety practices. Familiarity with the NEC is essential for anyone involved in electrical work, from electricians and engineers to inspectors and homeowners. Continuous learning and professional development are also vital in the field of electrical engineering. Staying abreast of the latest codes, standards, and technologies ensures that electrical professionals can provide the best possible service and maintain the highest levels of safety. In conclusion, a thorough understanding of electrical calculations combined with a strong foundation in electrical theory and a commitment to staying current with the NEC is essential for designing and maintaining safe and efficient electrical systems. Always prioritize safety and consult with qualified professionals when working with electricity.